I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for all the many students who came to this help session. And help, just I pray that you be blessed, that you would bless this session and just help us to make the most of the time, Lord. In your name I pray. Amen. All right, so like so many people here. It's great.
Okay, so...
I do the same if there were no students, by the way, just for kicks.
Really?
No, I haven't done that yet, but for a lecture I would. For a help session, I just feel like, all right, fine, whatever. So what was the question?
So 61
Uh-huh.
is the one where it was finding the rational functions that are represented by the series?
And this is mission 6. And complex mission 6, of course. Mm-hmm. Let's see here. Problem which one?
61.
Okay. All right, so how to approach this problem?
Well, I already did it.
Uh-huh.
One way. But my way was really, really complicated because I was like, oh, well, if it's just d to the k, then that is, I think it was like 1 over 1 minus d.
Uh-huh.
And I was like, well, let's try something over 1 minus d squared. And so then I did the thing where you multiply it and everything. It's like thinking backwards in my head. And then I did the same thing for the next one and just did cubed.
Ah.
And so I'm thinking that's the really hard way, but I think I
Well, yeah, well, here's how I would, so I guess the way I'd approach, like, let's take A. You've got f of x. I think what you were describing is, maybe a creative way to do it, which isn't necessarily bad. Let's see here. I'm not sure whether or not that's actually going to be more or less work than what I'm about to do. We'll find out soon.
For the first, the one with just k wasn't terrible. The one with k squared was kind of terrible.
Right. Yeah, that's fair. Now this one here, this one actually we can kind of understand if we integrate both sides. So the integral of f of x dx would be what? Dz rather. Yeah. Sorry. And so here this is a kind of funny integral I'm writing. I mean this to be a indefinite complex integral. So I'm engaging in the same practice that we engage in real analysis, in the sense that we use the integral sign both for the antiderivative and also for the actual process of forming a Riemann sum, which are conceptually rather different things, united in the fundamental theorem of calculus, as you know. But suppose I'm really talking about the antiderivative of that, then we have term-by-term calculus, right? And so what's the term-by-term integral of that? Well, I'll write it this way, right? There I'm using the term-by-term series theorem, which I almost proved this semester. It seems like I'm almost proving a lot of things lately. So z to the k divided, z to the k plus 1, right? Wait a minute. Oh, man. That's no cool. Ah, shnikes. That's not what I was hoping for. Dang it. Aw. Phooey.
Analytic.
Is what?
It's analytic.
It's analytic. Yeah. Yeah. I was hoping for those to go away and this just to be geometric. Because that's how I recall. Well, you know what I could do to make that dream come true? I should just make this k minus 1, right? K minus 1, multiply that by z, and then is that the same thing if I need to start this at 2? Is that right? Yeah, the first term then is what? K is 2z, 2z, you're right. That the first term, this is not, this plus z would be equal to the actual problem, right? Am I right? So I get, my first term is z, my second term is 2z squared. So I think if I factor out the z, I think that makes sense. And so then I think I've isolated a piece of it that I can do pretty explicitly and carefully, and then I can just come back with what I learn about that piece and put it back into here, you know? It's like this piece, this is nice. If I call this thing g of z, you know, I start to feel like maybe I made a typo also here, Bethany. I mean, because I'm not, well, we'll see. The problems make sense, whether or not I made a typo. But there might be a slightly related problem that is way easier to solve with the tricks I'm about to do. That may be the missed opportunity. Okay, so anyway, if this is g, then we can integrate term by term. And then what do you get? Integral of term by term integration gives me, you know, k plus 1. Then the k's cancel, and we're just left with the sum k equals 2 to infinity of, well, z to the k, right? Which is awesome because that's almost geometric. See, now I need to curses. This is just, I mean, so that would be minus z plus the sum k equals 1 to infinity, right? Z to the k. And so I've got, why don't I just not be a dummy and just, I don't even need to, I don't know why I'm doing that. I don't know why I'm doing that. This is just, I can just do that. Let's just write it out. What is this? This is z squared plus z cubed plus da-da-da, right? So this is geometric with initial term z squared and a radius of z, yeah? I mean, a ratio of z. So that's z squared over 1 minus z. So therefore, g of z is the derivative of the integral of g of z dz, right? Which is the derivative of z squared over 1 minus z. And so I can calculate that. 2z times 1 minus z squared times minus 1 divided by 1 minus z quantity squared. Maybe we can clean that up. You got yourself a plus z squared here. You got yourself a minus 2z squared over there. So it looks like we got a total of 2z minus z squared divided by 1 minus z quantity squared, I think. So then I can go back and plug that in, and I think that does it. So I got f of z. I'll write the z first. Z plus my z plus z times g of z, right? Where the g of z is 2z minus z squared over 1 minus z quantity squared. Now it's not clean yet, but you could clean it up and make it prettier looking, but that's a rational function. What did you get it? Did you get that?
Mine ended up being z over 1 minus
Z over 1 minus z squared. Huh. I like that answer. That sounds better than mine. Let's see here. What happens? If we make a common denominator, we've got ourselves a z times 1 minus z quantity squared plus 2z squared minus z cubed divided by 1 minus z quantity squared.
Yeah, that works.
Oh, you see it?
Yeah. Because it'll be plus z cubed, and then it'll be minus 2z squared, and then you're left with the 1 minus
So what's that simplify to?
z over 1 minus z squared.
Cool. Let me search for something for a minute. Let's see how me 4 years ago did it. If I can find it. That's not the right one. Doofus. Come on. I found the log z problem for when I assigned it from before. Didn't help us any. Come on. All right. Sometimes my notes to self are not helpful. Oh, look. Here we go. That seems less complicated than whatever I just did. I wonder. Remind me to readjust the camera in a minute or two. If I go over here and start doing something complicated, get lost in the math, I regret it. Let's look at how I did it here. Is it the same problem?
Yeah.
Yeah? Okay, so I didn't copy it down wrong. So what did I do? I factored out the z, and I'm a dummy. I don't need, I don't need to treat. I don't need to treat the k equals 1 case as if it's somehow separate. I mean, you see it, I complicated it by thinking k equals 1 needed to be separated out. The reason I did that is I thought they had like a division by z in it that I was trying to avoid, which is nonsense. It's not there. So we can just do it like I was doing it. Just keep the sum at 1, and then the, you know, that, oh, this is even better because we just go, oh, wait a minute, that's the derivative of this, which is that, which is that. Yeah, there's the weighted. And then this one, so, okay, this one here, I had to be sneakier. Does that make sense? I think that's what you're looking for, is this way, right? Yeah.
My second answer doesn't look like that.
Yeah, the k squared z to the k. Let's see here. Let's see. So after being successful with part A, and by the way, after about 2 pages of scratch work, I vaguely remember this was not something I just sat down and just did. This is after some work. I realized, oh, see, because in order to identify this as a second derivative, I need like that k times k minus 1. Because you got to think about like what does differentiation do to the power series, and you want to see the power series as like a second derivative. Because your goal in this game is to find series which are just formed from like z to the n. That's the technology we're working with. In principle, you could make your target other known series, right? If you're given a series and it's like kind of close to the sine series, modulo like a differentiation or something, then you could, like we're basing the chicanery off the geometric series, but you could anchor this calculational idea to other known series.
So are you assuming that the modulus of z is less than 1 for all? Like,
Oh yeah, yeah. Right, and you can get the ratio test will tell you the radius of convergence for these is 1. So what I do here, I changed my z to the k to a zk minus 2 by pulling out the z squared, and then I changed my k squared to a k times k minus 1, which is to subtract k copies of this, right? So having subtracted k copies of it, I added k copies over here, right? And then we're back to problem part A. So I already know that that's z over 1 minus z squared from the original part minus the z. That's from to keep the equality there. And then, of course, that's the second derivative of that series, which is second derivative of the geometric function, which we can twice differentiate and get down to that. So, and to give you the play-by-play after, I would say that everything was written here up to, this was written last, that was then wedged in, this was wedged in, that was wedged in, this was wedged in, and then I was too lazy to go get the whiteout to hide the fact that I added the subtraction by z at the end stage of my calculation. This might have an answer. It's from Gamelin. So maybe I looked in the back. I'm like, wait a minute, minus z. Hey, where's that coming from? So you can kind of like forward engineer, imagine yourself teaching complex analysis and you want to make a problem like this. What you do is you start with something like, some k equals 0 to infinity of minus 1 to the k over, 2k plus 1 factorial times, z to the 2k plus 1. And then like, that's sine of z. And so, I don't know, you could play games with this. Maybe, I guess the simplest game to play, if you wanted to like play this game of find the function which is the power series of. Just to show you the man behind the curtains, I could do something like this, cubed, right? And if I put a cube there, that makes this (3k plus 3), right? And then if I differentiate this, what happens? You know, and then you could say, okay, so find a function which this is the power series representation of. All of a sudden, you haven't worked very hard to come up with a problem that is quite challenging for students to solve. Like find the function which that's the power series for. Like I can tell you from what I wrote on the board that it's, 3z squared cosine of z cubed. That's the power series representation of that, which is easy over here. I mean, this step is easy, that step is easy. I'm probably off my... Yeah, no one could see what we were doing. But yeah, it's a game you can play. This also equally well implies, if you're teaching like an honors section of like say Calculus 2, you can play these games too, like the Taylor series stuff. Like say, find the function which that's the Taylor series of. It's, you just got to have like an intuition for it. I mean like there's kind of smoking guns here, right? Like this factorial in the denominator, it stinks of a trigonometric function. And it's alternating, so that tells you it's sine or cosine. In the absence of that, I would be hunting for Cauchy sinh. In the presence of that, I'm thinking sine or cosine. And then the other things, when you see something like this and that, it stinks of differentiation because you got like 1 power less, 1 power more. You can see something's been differentiated. So you can, so you could try to integrate that and then see if the thing that results is something that you know. But anyway, I don't know if I was teaching honors versions of this and I had, 50% of my time to sit around and come up with problems that would be hard for students to solve. This would be one of the things I did. But anyway, you got other questions?
I have a question about that. The derivative of 1 over 1 minus c, wouldn't that have a negative?
Oh, well, it would, except the chain rule. So the one chain rule...
Oh, never mind.
Okay, you got it. Mm-hmm.
So part B of 60,
Uh-huh.
it kind of like looks complicated,
Let's see here. Yeah, find the disk and radius of convergence for the following pairs. By the way, the thing I shortchanged in class today was talking about how, like, for a given complex function, sometimes there's some kind of like boundary you can't analytically continue past. So that's in my notes. I give examples of functions which it's impossible to like escape through the boundary because there's like some dense set of points which are like singular on the boundary or something like that. I mean, I hope I at least gave the impression that, you know, there's more to learn. I think I hopefully communicated that much. My notes have a different focus than what I was doing today, though. Okay, so z minus I over 2 to the k. So the way I would... Oh, part what?
Part B.
Oh, part B. Okay, so z plus 5I... You have to... Can you read it for me?
Plus 5I all to n times n plus 1 squared.
N plus 1 quantity squared. And that's summed what? 0 to infinity? And this is my f of z or something? Or I didn't even give it a name. I didn't even name it. So we want to do what? We want to figure out what's the radius of convergence? Okay, so I usually look at, I think of this thing as being my a sub n. And I'm trying to remember, I think I want to look at a sub n plus n over n plus 1, or is it n plus 1 over n? I can't remember. Goodness gracious. Do you remember?
I got one, so I don't think it will matter. But
Oh. Well,
so you have to do the whole thing. You don't just do the part that looks like an A and like the n plus 1 squared.
well, you know, there's different ways of looking at it. If I can find it eventually. That was back when I was simpler times, right? Come on. That was before is it before the Weierstrass test or after Weierstrass?
It was at the end, very end of the section.
Hmm.
The very end.
If it'd be more, if I had, you know,
Oh, I think it was at the end.
say labeled it as, I don't know, the ratio test, that might have been helpful. But I did not. It's just theorem such and so forth in here. Right?
You get
There we go. A sub k over a sub k plus 1. You're right. So we can just look at the coefficient if we like. What I sometimes think about is just that, I mean, if you fix z and you think about the numerical ratio test, it's not illogical to use the whole thing as the a sub n.
Do you have to or
No, you don't. I mean, this theorem, the ratio test in the notes says that it suffices to look at the quotient of the a sub k's. Where you'll get into trouble is if you don't actually have z minus z naught to the n. Right. But we do here, so we're okay. So a sub n is n plus 1 squared then. I see. So a sub, I've already forgotten. A sub n over a sub n plus 1. I better get my act together. I'm teaching Calc 2. Oh, I'm teaching it right now. I'm teaching Calc 2 online. Yeah, it's happening. It's real. Yeah, you're right. That goes to 1.
Wait, it would be n plus 1 over n plus 2 though, right?
Yes. Yes. Thank you very much. Do appreciate that. But yeah, that goes to 1. Now, what does that tell us? Right.
I just want to make sure. It's
Yeah.
kind of too easy. But
No. Right, therefore, radius of convergence equals to 1 for this. Let me show you what I was talking about in the notes since you're here.
And then that means that the disk of convergence would just be where the modulus of v plus 5i is less than 1, right?
Right. So this f of z converges for all z in the complex plane with z plus 5i less than 1. Yeah. So I think my notation for that has been the disk of radius 1 centered at minus 5i, and it's fuzzy, so I think I put a 0 up here, right? Now, question. I mean, those points in the interior of that circle, given to be points of convergence for the series, are there other points of convergence on the edge? You know? Is there a point of divergence on the edge? Like, what if I look at the modulus of z plus 5, if I look at points with modulus of z plus 5i equals to 1, right? Does it diverge there? I think yeah, because then you'd have your term. We could say, you know, z plus 5i equal to, you know, let's say e to the I theta, right? And so then my a sub n would be, well, not a sub n. Let me call this whole thing, I'll call it b sub n just to give it a different, because we used a in a different sense. Fine. So b sub n would be n plus 1 squared times e to the e to the what? Not e to the I theta to the what? To the 2n. So that'd be n plus 1 squared e to the 2i n theta. What happens is n goes to infinity for that. Nothing good, right? The coefficient in front blows up, and depending on what theta is, it might either keep going all the way around the circle, covering all possible points densely, or if we had theta equal to pi, if we had theta equal to pi, that could just stay at 1, right?
But if you look at that, does it not matter that it could be like geometric? Because like once you hit 1, then it couldn't be geometric anymore.
Once I hit 1.
Like the modulus of z plus 5i.
Yeah.
And it's being raised to the power of n, so then don't you know, like as soon as it's greater than 1, that it's not going to diverge because you're not even dividing by anything?
Well, but this is not a geometric series, right? But you're right, it diverges. I mean, whatever your intuition is about it diverging, I wouldn't argue, because it does diverge. But if it was a different problem, right? Like if instead of this one, we had division by n plus 1 squared, right? This problem, very similar, right? Very similar looking. I don't need these. What's wrong with me? So you're, yeah?
So like, okay, never mind.
So the funny thing is, when you look at a sub n over a sub n plus 1, what do you get? Right, you get, I think you get n plus 2 squared over n plus 1 squared this time, yeah? You get the reciprocal of what we had before. It just goes flippity floppity. It still limits to 1, right? As n goes to infinity. So by the ratio test, you know, you still have the same disk of convergence, open disk of convergence. We just proved, actually, by the nth term test that every point on the edge of this, if I haven't done something stupid, disk of convergence is divergent. So this thing has a hard boundary, like it's every point on the edge is divergent. I think this one is more nuanced. If we look at the place where the modulus of z plus 5i is equal to 1, I think more interesting things happen for this one, right? What happens for this one? Well, like if we have, for example, if we have z plus 5i equal to 1, that would be on the edge, right? In other words, I'm saying particularly the point z is equal to 1 minus 5i, right? You plug that in, then if we look at f, so in other words, look at f of 1 minus 5i, well, that's what? That's the sum n equals 0 to infinity of 1 over n plus 1 squared, which is pi squared over 6, right? Because that's the p equals 2 series, which we know converges. So there's one point of convergence. And also, minus 1 works. So what would happen if you look at like an arbitrary point? I think, so if you set z plus 5i equal to e to the I theta, that allows us to sort of analyze an arbitrary point on the boundary. And then we can go back to the nth term test, I think, for this one as a means of analysis, right? So you're looking n equals 0 to infinity of what? E to the what? E to the 2ni theta, much like we did last time, right? But this time divided by n plus 1 squared. Goodness, I think this one, I think every point on the edge converges. Because you could do squeeze theorem. As n goes to infinity, you can bound the exponential e to the 2ni theta, can't you? For fixed theta. Theta's fixed here between 0 and 2 pi. No, the modulus of e to the 2ni theta is between plus or minus 1. We can squeeze theorem that thing to 0. I'm sorry. A sub n going to 0 converges, does it? Right? But we can do a comparison test, right? You can compare that series to, I think you can still prove it converges by like comparison to p equals 2. I'm a little worried about the oscillation though. Does that oscillate? But even though it oscillates, the denominator is getting very, very small, so it seems like it's just kind of a herky-jerky alternating series of sorts, yeah. I'm pretty sure that converges. Everywhere, yeah. Now, if you did like 1 over n, What if instead of having 1 over n plus 1, think about this same example, right? Erase the 2. Still got the right? And okay, great. But now, right. But if I put minus 1, then I get minus 1. Oh, and I also need to erase the 2. So then I get minus 1 to the n. So I got log 2, alternating harmonic series. Yeah. And yet I have a strong suspicion that that might be the only point on that one that it. I mean, anyway, I warned you guys about this in class, that if you start analyzing what happens on the at the actual radius of convergence, it can be very complicated. Here I have examples, in fact, in the analytic continuation section about precisely this issue. See this example, 10.9.3? If you look at this, that's funny. Why a z at the start? That's man, that bothers me. I want that to be a 1. I wonder if that's a typo. Anyway, so the sum of even powers, you can show that the radius of convergence is 1. I kind of believe that because, yeah. And you can argue that this goes to infinity as z approaches any even root of unity. Let's see here. Does that make sense? Any even root of unity. What would be an even root of unity? Minus 1? Is that even root of unity? Even root of unity. So like the square root of 1, or the square root of the fourth root of 1, or, well, rather, anything, z in 1 to the 1/2, or z in the, the quarter powers of 1, etc. So like, well, certainly if you put z equals to 1, that thing diverges. And if we put, and if we put an even root of unity, then those all power to 1. And you can argue that the even roots of unity are dense on the unit circle. So that means that this function's unbounded at each point on the unit circle, and it follows that the unit circle is a natural boundary of this series. If you were to try to analytically continue the function defined by that series past the edge, you couldn't do it. You get stuck on this natural boundary. This one, which is kind of like what we were just looking at, centered at 0, converges for each z with z equals to 1, except z equals minus 1. Ah. So only at z equals to minus 1 do we I see if I put in z equals to 1, I just get the alternating series, and that converges. And I see that if I put z equals to minus 1, I get the harmonic series, which diverges. What's not at all clear to me is why, if I pick other complex things around the circle, why those converge. But this example is saying that if you study it, you can prove that they converge. So this, if you define the function by this series, then you can apparently analytically continue away from the original disk in any which way you like, except don't get too close to that, because it's a singularity on the boundary. And then this one, Lucen, in 1911, found a series with with coefficients which go to 0, all right, and yet it still diverges at each point on the unit circle. So like this example was pretty lazy. It has all of the coefficients not going. I mean, it's clear that that diverges because of the nth term test. This, on the other hand, fails. The nth term test is no help, and yet it still somehow diverges at every point on the unit circle. And then continuing this story of weird examples, Sierpinski, 1912, produces a series which diverges at every point on the unit circle except z equals to 1. And this book I mentioned, Ramir's book, it's another great book to read past what we're doing if you really want to like read a lot of interesting history, and it's just a fun read. A lot of the more interesting points in my notes are from that book, if not from Game 1. Anyway, you had other questions, I think, maybe? Maybe not, I don't know.
Well, I guess I kind of had a question about 55.
Uh-huh.
It was my first, if you recall that, is really, really short, and I feel like it was maybe too easy, but
Oh, no.
it seems like it's true.
Yeah, I don't think the proof of that has to be long.
Because I said that if that converges to C,
Mm-hmm.
then for every epsilon during the year, there exists an n in natural numbers such that the modulus of this series minus C
Uh-huh.
is less than epsilon for all n greater than that n.
Now, does your proof involve partial sums?
Oh, yeah.
Okay, I thought you meant that, yeah.
Yeah. The series, or the, from j equals 0 to n
Mm-hmm.
minus the C
Right,
is less than epsilon.
right.
But then the modulus of that equals the modulus of the conjugate, like the whole thing, but then I think because it's just subtraction, you can just do like the modulus of that and the modulus of the other, right?
Right. So I think if you wanted to be, I mean, here's the complete proof. Let epsilon be greater than 0. Since, I think I'm just going to write what you just told me. Since the sum k equals 0 to infinity, was it c sub k? Is equal, oh, c sub j. C sub j, there exists n in the natural numbers such that n greater than or equal to n implies that the modulus of the nth partial sum is less than epsilon. Let n be greater than or equal to n. Consider modulus of the sum of cj bar minus c bar. Well, one of the properties of the complex conjugate is that that's equal to the I mean, there's various ways to package this, but here's one way you could. So I can take the complex conjugate of any complex number, and it does not change the length, right? Since the length of w is equal to the length of w conjugate for all w in the complex numbers, right? But then, and then here's where you could, in principle, supply more proof by a careful inductive proof. Well, I guess not yet. Then this is, of course, the complex conjugate of the sum. And then the complex conjugate of the complex conjugate. And then by, you could prove with induction if you want to be more fussy, but I'm fine with you not doing that. This, of course, is the sum. J equals 0 to n C conjugate conjugate j minus, C conjugate conjugate. But of course, the conjugate of the conjugate is the thing again, as we talked about in abstract today, right? It's an automorphism of order 2. And so you got Cj minus C, which, by the way, is less than epsilon. So therefore, the limit as n goes to infinity of the nth partial sum of the conjugate series is equal to C conjugate, which is exactly what we set out to prove. Yeah. So I agree.
Kind of had one or two,
It's
maybe one step that's left out.
when I originally, like my first approach to this, I didn't have it all in one flowing calculation. I had like a couple of before steps. Like the other way you could attack this would be just to show that, essentially just to show that this inequality less than epsilon follows from that one. And you could break that up into a couple sentences. This is not the unique correct proof for this or anything like that. Also, if you already had properties of limits and conjugates settled, then that would be like another way to do this, right? Because essentially, well, but I tried to not allow that by writing that I wanted an epsilon n proof, because otherwise you could just appeal to properties of limits. Like the limit of the conjugate sequence is the conjugate at a limit of the original sequence. If you have that theorem, and then you just apply it to the sequence of partial sums which exists, this theorem also follows. But anyway, that's it?
For my question?
That's it for your questions?
Yeah, I'll go.
All right. This help session is concluded. All of you, many students, may go home now.